Welcome to another episode of the Tech Exception Show. My name is Ruth Yakubu, and today we have a very exciting startup joining us today. I have Jon Herlocker, who is the CEO of Tignis, and today we're going to be talking about upgrading advanced process control from advanced. Today we're going to be talking about upgrading from advanced process control to AI process control. I always get tongue-tied. But we have Jon, who is the CEO of Tignis, joining us today. Jon, welcome to the show.
Thanks for having me, Ruth.
Awesome. So Jon, tell us about Tignis. What problem are you trying to solve?
Yeah, thanks. Again, thanks for having me. So at Tignis, we offer software solutions to companies in the industrial and manufacturing space, and specifically solutions that help them take either small steps or large steps towards more autonomous plant operation, right? Using things like predictive analytics, AI, and machine learning. And core to our approach is this idea of integrating physics modeling with AI and machine learning. And I guess to briefly talk about the problems that we're solving, you look at today's automated plants, or automation within today's industrial manufacturing plants is relatively mature, shall we say, right? It's either sort of simple reactive controls, or what used to be what called advanced process control, which is not particularly advanced these days. And so there's this whole new generation of AI machine learning that way we have discovered ways to apply it to the concept of process control, and yielding sort of systems that can have much tighter process control, i.e. they can stay much closer within the boundaries of what you're trying to produce, whether that could be an oil refinery or that could be a semiconductor wafer. And if you can sort of produce much tighter, reduce the variation in your process, then you can either yield more or yield higher quality.
Awesome. So the way I see it, it seemed like the advanced process control is more of an analytics, more on the physics side of things, instead of the AI, the way manufacturers do their process control.
Yeah, now it varies a bit from sort of industry to industry, but take, for example, oil and gas refining. Today, what's seen of as advanced process control is often some sort of chemical engineer who comes into a refinery and spends a huge amount of work to build a model of what's supposed to be happening in this plant, and based on that physics model, predicting settings that you should maybe tweak or set in the plant. And so that's, it has lots of weaknesses. It's custom to specific plant. If the plant changes over time, which it does, those models become less accurate. And fundamentally, they simplify the model to make it work in the first place. And so all of those lead to errors. And we've found that with AI and machine learning, you can dramatically improve both the quality of sort of your control, but also its robustness to change in the plants themselves.
That's awesome. So speaking of AI, how do you utilize AI and machine learning in your processes?
Yeah, absolutely. So, well, we use it in a variety of ways, but I'll talk about a couple of them, and I might be jumping ahead a little bit too, but in general, we take data we take this sort of time series data coming off of the different sensors on the plant, right? And you can think about, building predictive models that take all those input data and predict kind of outcomes that are desirable, or et cetera. And so one way to use machine learning is to build those relationships between sort of the systems that physical properties you're monitoring the plant and the outcomes that you're trying to get to. But we also have some really exciting things around digital twins that I'd like to tell you about today that have to do where we can actually take those physics-based models and use AI and machine learning to make them a lot faster.
Okay. So you mentioned using sensor data. Are those the only types of data that you collect? Let's say you're to have a new client that falls in the industrial or manufacturing plant. Are sensor data the only types of data that you collect?
Not at all, not at all. I mean, a huge amount of the opportunity comes from the proliferation of real-time sensors. So real-time sensor time series data is a critical part of almost every solution, but it's not the only solution. I'll give some examples. So for example, in oil and gas, like if you're optimizing an oil refinery, you care about not just the time series data, but you also, excuse me, you might care about lab data, right? Lab measurements that are happening about the data. You might care about the financial data, right? Like the outcomes that are happening related to that plant. You might also care about the sort of the quality of the crude oil coming in. In many cases, those peripheral data do not come in nice time series data. Also, like we do work in semiconductors. I'll tell you a bit about that. In the semiconductor space, we have not only is there time series data, let's say the temperature data coming off of a chamber on a tool, but there's also a lot of batch data, right? I have a batch of wafers that kind of work their way through, and that comes in more of a relational kind of form, right? Like this batch went through this system and it had these outcomes, et cetera. And then I'll actually mention another one that we see a lot of, which is image data or image-like data. And so in semiconductor, again, you have lots of pictures being taken from above, whether cameras or electron microscopes. You also have fault patterns, which are sort of like, they're like images, but it's basically just points on a wafer for which faults are happening. And those are very critical. And so we've built a system that can ingest data of all these diverse things, not just time series data, but also image data, but also the kind of data you might get out of a manufacturing execution system, which tends to be a bit more relational structured data.
So not only are you guys using time series data for, I can understand using that for anomaly detection, but are you guys also using, let's say, for imaging, identifying faults? Are you guys also doing predictive maintenance for some of the faults that you're trying to identify?
Good question. Yeah. So we actually, our goal is to help customers achieve this next generation of, process control, of autonomous plant operation. But it's a journey, and to help customers along the journey, we have a product offering that is really about helping customers to take that historical data they've collected and to discover the optimization, opportunities within that data, right, which they can then, start with that. And that includes very commonly predictive maintenance, right? I need to get a better understanding of how my equipment's operating. It needs to be up and running before I can really make it more autonomous. And then also from there, they go into often production optimization. I want to start to understand, what are the possible places which I could see a huge improvement through advanced process control or through more predictive process control. And so we designed and built our own analytics language, which we call the digital twin query language. And the whole goal of this language was to close that gap from, hey, I've got all this historical data, whether it's sensor data or image data or whatever, stored for like root cause historical analysis. How do I turn that into sort of forward-looking, predictive value? And predictive maintenance is a very common one there. Sometimes just production optimization decisions around oil well fields, like I want to decide when to, tweak the oil wells to ensure they keep flowing over time. Or in sort of oil refineries, they might use it for virtual sensors. And so they have maybe a lab measurement, which is very hard or expensive to compute, but you can kind of reconstruct what it should be as using a predictive model from other things you can measure about the system. All of that stuff we do enable, and we do kind of help people through those use cases. And of course, the idea is that as they become more confident with the value of their data and the value of predictive analytics, then they'll invest in more, aggressive opportunities like process control using AI.
You mentioned using historical data. Is that very common for every client that you go into that they have historical data, or do every client have in their workflows have sensor data? Because when you're talking about predictive analysis, I automatically think of the remaining use of life.
Yeah.
So with that, sometimes you need historical data, sometimes you just need, okay, when did things fail? And let's learn from failure, that sort of thing. So what are the different scenarios that you walk in for the different clients that you deal with?
Yeah, it's a great question. So when you're using AI and machine learning, it's machine learning, right? So you have to train a machine to do something. Therefore, you need training data of some kind. Now, the good news is, a lot of industries have already been collecting sensor data for, some number of years, right? Particularly the high value process industries. So we have two real target markets that we go after. One is sort of a broad market, and it is customers who use the OSI Soft Pi Historian. And the OSI Soft Pi Historian is like the leading database, or they call it a historian, for industrial data. And this is what you find in places like pharma manufacturing and oil and gas plants, et cetera. So in some sense, by our choice of target market, we are going into places that have good amounts of historical sensor data by definition of being in that market in the first place. And likewise, we also do a lot of work in the semiconductor space, and they have, just because they are such a data-driven organization to begin with, they have huge amounts of data to start with. So yes, we work with industries where there's large amounts of data, and part of our hypothesis is going forward is the number of companies that collect and store large amounts of data is only just going to just skyrocket. It's cheaper to store it, it's cheaper to collect it, et cetera. And so we are really focused on kind of the missing link, which is how do we go from having collected all that data to actually getting value out of it. And yeah, some of the use cases, and you mentioned some of the use cases that people are interested in, and we give them tools to and recipes to do things like predictive maintenance. You mentioned remaining useful life as well as one of those use cases, but we also do it around production optimization. Those are really the two categories we see the most of.
Wow, that's awesome. And it's also good to know that depending on the industry that you're targeting, there's also data already out there for some of the use cases. So when it comes to identifying faults or degradation, doing fault classification, finding problems, do you guys use any open source tooling? Because I can imagine using a lot of visualization to weed out all the noises, or figure out what features, because if you're collecting a lot of data from, let's say, sensors or pipes or you name it, there's going to be a lot of data. So how do you figure out which features are important to feed into your algorithm, machine learning algorithm?
So I'll take two questions really there. One is like, what is our use of open source software kind of, and I think we're like every modern, startup company created last, which is there's a lot of fantastic open source libraries, open source systems out there that are extremely well tested and robust, and it doesn't make sense to build yet another, right? So we're not going to go build another database, right? There's plenty of those out there. We can use open source ones for that. And in fact, even on the AI and machine learning side, there's these low-level systems like TensorFlow. So if we use TensorFlow, for example, it's not the only system we use, but it's one of of several systems that we use as a way to deploy AI and machine learning analytics. So I guess, do we use open source? Absolutely, right? We want to be good at what, we want to provide that value layer, which is really about, we built this next generation analytics language that runs on top of all these things. That's proprietary. We built our own sort of digital twin acceleration technology. that takes these sophisticated finite element models and makes them sort of near real time. That's proprietary technology. So I guess, yes, lots of open source in addition to proprietary stuff that we build. That's kind of step one. The second question is, like, how do we, that's a really hard question. Like, you've got all this data and you're building a predictive model, and the question is, what do you feed into that model? Like, I want to predict, I want to find a way to predict what the financial output of this refinery is going to be, over a period of time. What variables do I feed into that? We have two ways of handling that. One is that, again, we believe very much in sort of merging a deep understanding of the physics and AI machine learning together, right? And so one way to figure out what features are important is to have some understanding of the physics that go into that process, or the chemistry that goes into that process. And if you examine the equations of the physics, these are the things that should affect that, right? It's quite straightforward. That being said, sometimes that information is hard to achieve or not available. And so we'll fall back on more statistical feature importance kind of techniques. And, it's a pretty data science, deep technical question. And I know that our data scientists actually have some algorithms they use that will automatically kind of recommend sort of the most prominent features, in an algorithm. But I guess I don't know that I could share the exact details of which product they use, or whether they wrote that themselves or they're using an off-the-shelf thing. I'm not sure.
I totally understand. So how does, since you're gathering a lot of data, how does computing look like? Because for me, I see this as a continuous iterative process that is very high critical. So you're crunching all the analytics, deploying it, and seeing what happens and coming back. So can you walk us through your process of what environments, how you create your experiments?
Yeah, absolutely. So we started out as a SaaS company and purely based on the Microsoft Azure cloud. We extensively use kind of the Azure infrastructure as a service, and particularly the Azure Kubernetes service. So our whole ecosystem runs on top of Kubernetes, and we've been a long time user of the Kubernetes service for Azure. So that's part one. But the whole software infrastructure was built kind of above that Kubernetes layer intentionally so that we could take that same package and deploy it on site, because, as you might know, Ruth, a lot of these manufacturing plants and semiconductor plants have not fully bought into the cloud, right? They're like, we're a little sensitive about that. And so all of our software actually can kind of be extracted out and then sort of run on site as well too. Having said that, we also take advantage of sort of Azure's machine learning kind of services, particularly at the design phase. And so, as I mentioned before, we have this really sophisticated digital twin technology where we can take a high fidelity physical simulation. This could be a finite element model. It could be a computational fluid dynamics model. It could be a high fidelity process simulation. And we'll build sort of an AI, a surrogate model for that. That's a machine learning model that emulates the physics model, but does it like potentially millions of times faster. For those kind of development, we're doing huge amounts of training and stuff, and we'll take advantage of Azure's sort of GPU clusters and their machine learning services in the cloud to construct those models, which may then get deployed in an on-premise sense in our Kubernetes cluster on-premise. I will also say that we're doing some early experiments with the Azure Stack Edge. And so we're that's pretty exciting to us as a way to possibly reduce the friction significantly of our on-site deployment. But we're not currently dependent on it, but we like the idea. It could speed things up a lot for us.
That's for sure. That's good to know. So speaking of simulation, you have your model, you built it out. Let's talk about the digital twin, because you are building a physics model of a replica of what's out there in the plant, and you're infusing this AI model that you created. How does Tignis go about creating this? How does the process look like?
Yeah. So right, as you know, as it's sort of becoming clear, we have a variety of solutions, right? That we have sort of a general analytics language to help people sort of discover the possibilities. But one of the pieces we really believe that bringing physics and machine learning together is the way to create the optimal outcome. And there's certain processes that are complex, right? And the only way you can really understand what they're going to do is by building a physics model of it, right? Where you're modeling like the particles and the way they interact with each other. And these models are fantastic and amazing what they can do, but they're also like incredibly computationally expensive, right? They just, you have to model interaction of every particle or every section of the pipe with every other section, or every blob of fluid with everything around it. I mean, it's incredibly expensive, and just one time step can take a long time. So that's kind of exciting, but also really blocking, right? If I want to now use this, so I can have myself a digital twin, which is a physical simulation of a virtual simulation of a physical process, and I can sort of ask it what if questions. What if I change this? What am I going to see? That exists today when you have those high fidelity models built. It's just too slow, right? Like maybe I ask it for one time step and 30 minutes later I might get an answer, right? So we have a process where if you have that model, the high fidelity simulation model, or you want us to create it for you, because we also have engineers and data science or PhD physicists who can create those, or chemical engineers who can create those models for you. You have that high fidelity model, but you want to use it in a more operational context, right? I want to be able to say, without waiting 20 minutes, what happens if I change this, right? I want like a second turnaround, because literally the plant's operating. It's not going to stop and wait for me. How does that work? And so we've developed sort of some technology and capabilities where we offline will run that simulation, that very slow simulation, to generate some training data, right? Which we use to feed to feed kind of our machine learning engine, which learns kind of a model of what that simulation represents, but is incredibly more optimized, right? And this doesn't work for every possible simulation, but it works for a lot of them, right? And when it works, it really enables this use case. It just wasn't possible before. Instead of one sort of simulation every 20 minutes, maybe I can do 100 simulations a second, right? And think about now, if I can simulate 100 futures or 1,000 futures per second, I can just pick the one that's going to have the best outcome. Oh, this one's going to be the best, so let me set the dials to reach that particular outcome. So it's pretty exciting breakthrough stuff that we're doing that really expands sort of the places that digital twins can actually become applicable in sort of real-time operational settings.
That sounds very exciting, because I feel like for any business, before you invest your dollars into trial and error, because I think of those commercials with the crash dummy, where the cars that keep slamming into the walls. I always wonder, okay, how many, let's say, BMW cars it took to do those tests.
Yeah.
In real life, it takes a lot of money and costs. So it seems like digital twins kind of prevent that overhead, where you can test with a simulation before you commit your investment dollars into actually implementing in real life.
Absolutely, and you can use them at design time, right? Like you said, but you can also use them now at operations, where you're like at every step you're making a decision about every second. How do I want to set the dials for the next 5 minutes, right? Well, let me just simulate all the futures and pick the one that's best.
Awesome. Well, it looks like we're 3 minutes to time. So, Jon, this was an amazing conversation. I really appreciate your insight. Do you have any parting words, especially for the manufacturing or industrial world, when it comes to the future of AI? Where do you foresee this future of using AI in the process that they use for end-to-end simulations?
Yeah, I mean, if you look, over AI-powered optimizations are, you can see this from reports from McKinsey's and others, that AI is driving companies' revenues up and driving their costs down. And so AI-powered, autonomous operation and plants will dramatically improve companies' revenue, will decrease their costs. And so I think the trend you're going to see is really just a separation between the companies that do it and the companies that don't, right? And the companies that do it are going to see their profits rise and their robustness to change increase, and the companies that don't are going to increasingly fall behind. And so that's my forecasting for what you're going to see over the next 5 to 10 years, is that certain companies are going to adapt and invest in this kind of tech, and they're going to increase their lead over the competition. So I encourage people to choose the right path.
Awesome. Well, this is awesome, Jon. Tignis is definitely on the cutting edge in the manufacturing world, and I really appreciate you have coming on the show. And we look forward to, for the audience watching the show, we look forward to having you guys next week. Thank you.
Thank you, Ruth.